thermochemical equations are chemical equations that quantitatively include heat. So the heat is written as a reactant or product, just as we saw the examples for endo and exothermic reactions. We have something with a thermochemical equation called standard states. And standard states refer to the following set of conditions: a concentration of 1 molar for aqueous solutions, a temperature of 25 degrees Celsius or 298 Kelvin, and a pressure at 1 bar. Okay, remember 1 atmosphere is equal to 101.3 bar. So if we wanted to relate 1 bar in terms of atmospheres, 1 bar would be equivalent to 9.87 times 10 to the negative 3rd atmosphere. Okay, so that's the relationship there. With thermochemical equations, we have the term standard heat of reaction. Okay, and we're going to define what standard heat of reaction is, and then I'm going to show you we're going to go back to a thermochemical equation and do some things with those equations. Okay, so thermochemical equations, standard states. Okay. Right, and remember, you can always go rewind, and pause if you need to stop at a certain point or hear me say something again. And it's a good idea to keep taking the notes like as if we were in lecture, so you have that record of, of the material, because you're going to take Chem 122, and this way you have that full set of notes from 121 as a good reference. Okay. Standard heat of reaction. Okay, is designated delta H with a little degree sign. Okay. And this is the value for the enthalpy change for a reaction under standard conditions. And involving the actual numbers of moles that are specified by the coefficients of the equation. And the degree sign is used to show that it is standard conditions. Remember, you have the balanced equation and you have the coefficients representing the moles of the reactants and products. And then you have a thermochemical quantity either as a reactant or a product. We're going to see a little bit more about that. Okay. The degree sign is used to show standard conditions. Okay. So the thermochemical equations, as we've said, okay, it shows the amount of, it shows the enthalpy quantity, and it also shows the states of the reactants and products: liquid, solid, liquid, gas, aqueous. Okay. So I'll put that on the screen for a moment there. Okay. Thermochemical equations show the value of the standard heat of reaction and also give the physical states of reactants and products. The standard heat of reaction value that you see in the thermochemical equation only holds true when the coefficients of the reactants and the products are taken to mean the moles of the corresponding substances. Oops. So because the coefficients, mean moles, we're going to see that when it comes to thermochemical equations, sometimes we need to take those whole numbers and reduce them to fractional coefficients. And I know that when you learn how to balance equations, that's a big no-no. You're told you can't use fractions. You only have to use the lowest set of whole numbers. And then we get to thermochemistry and we say, okay, yeah, you can now use fractions. Okay, so let's see some problems, some examples of what these terms mean. Okay, these thermochemical equations, we saw examples with exo and endothermic reactions. Now let's look at them again and apply some of these other terms that we have mentioned here. Okay. Let's take two thermochemical equations. Let's take two combustion reactions. Let's take the combustion of methane to start off with. It's pretty straightforward and easy balancing there. And then let's look at the combustion of octane, okay, which is in gasoline. All right, so first we'll take the lower hydrocarbon, the methane, and then we'll take the higher hydrocarbon, the octane. All right. combustion of methane follows the thermochemical equation below. Methane gas with 2 moles of oxygen gas produce carbon dioxide gas, 2 moles of water, and 802 kilojoules of energy. Okay. So for every 1 mole of methane that reacts, this is how much heat energy we get. Okay? Well, what if 1 mole doesn't react? What if half a mole reacted or a quarter mole reacted? The amount of heat that would be produced would be directly proportional to that, because you would treat this as a mole ratio. When we do stoichiometry, the mole ratio for methane to water would be 1 mole of methane produces 2 moles of water. Well, 1 mole of methane produces 802 kilojoules of energy. If we had a half a mole of methane, then we would have half of this heat quantity form. So 401 kilojoules would form. Let's work that out. Okay, so what is the thermochemical equation if only a half a mole of methane reacts? Well, what we would do then is we would divide all of the coefficients, which represent moles, okay, by 2, okay, and including the heat quantity as well. Okay, so then we would have 1 over 2, which is 1/2 methane gas, plus 2 divided by 2 would be 1. Okay, so we wouldn't write the coefficient of 1 mole of oxygen gas. Okay, 1 mole of carbon dioxide, we divide that in half, would give 1/2 mole carbon dioxide gas. And the 2 moles of water would turn into 1 mole. And then the heat quantity would be 401. Okay. So the heat quantity follows the same rule as a mole ratio. Okay, you would treat it as if you were manipulating a coefficient of a balanced equation. Okay, you would treat that the same way. Okay, so you say, all right, fractional coefficients, that's something new. Yeah, with the thermochemical equations, we can have the fractional coefficients. And when we go to the next lesson, Hess's law, we're going to see that. Okay, all right, let's look at another thermochemical equation. Okay, let's look at the combustion of octane. Okay. So you see, any fuel that you have, it produces carbon dioxide. Okay, hear about fossil fuels producing carbon dioxide. This is the chemical reaction for combustion. Okay, carbon dioxide is produced. We're going to see that the higher carbon content you have produces more carbon dioxide and also produces more heat as a result. Let's look at octane, for example. Octane has 8 carbons. Okay, so we're going to do example 2. The combustion of octane follows the thermochemical equation below. Okay, remember, octane is one of the components in gasoline. Okay, so we have C8H18. Okay, yes, it reacts with oxygen gas. Yes, it produces carbon dioxide. It produces water. And guess how much heat is produced? 10,148 kilojoules. Some references may have it, the heat amounts slightly different with the decimals, okay? Let's balance this equation. Well, let me give it to you balanced because it's a little more time involvement there. Let me give you this balanced equation. We would have a coefficient of 2, a coefficient of 25, a coefficient of 16, and a coefficient of 18. Okay, so for every 2 moles of octane that react with 25 moles of oxygen, we get 16 moles of carbon dioxide, 18 moles of water, and over 10,000 kilojoules of heat energy. Okay. So let's change this problem. What is the thermochemical equation if only 1 mole of octane reacts? All right, so here again, because the relationship's 2 and we want to know, divide this again in half because we have 2 moles and we want 1 mole, so dividing by half. Again, we would divide all the coefficients by 2 and then we would divide the final heat, the heat value by 2 also. So that would give us, it's not always going to be divided by 2, but the examples that I'm showing you just happen to be that. Let's get our new coefficients and our new heat value. Okay, so 2 divided by 2 would give just 1 for the octane. The 25 divided by 2 would give 25 halves. Okay, the 16 divided by the 2 would give us 8, and then the 18 divided by the 2 would give us 9, and the resultant heat would be 5,074 kilojoules. Okay. So now if 1 mole of octane reacts, we're going to get 5,074 kilojoules of heat that are produced as a result of that reaction. Okay. So the main point we want to get from this is that we treat that heat quantity, whether it would be in an endothermic reaction as a reactant or in an exothermic reaction like the examples I showed here as a product, you treat that as a mole quantity in terms of the relationship with the reactants and a product. Just like you treat this, 2 moles produces 18 moles, okay? 2 moles produces over 10,000 kilojoules of heat. 1 mole produces a little over 5,000 kilojoules of heat. Okay, that's the main idea that we want to get there, get out of this. So when we go to Hess's law in the next video, we will be seeing thermochemical equations, with fractional coefficients and with heat quantities that are part of them.